Okay, so ADH or vasopressin, what does that do when it is secreted by the hypothalamus? How does that help us with low blood pressure and low blood volume? Well, ADH will target the distal convoluted tubule and collecting duct. So we're at the end of the nephron, so we're fine-tuning this urine that we're making, right? So if we look at this picture, here's my nephron tubule, the distal convoluted tubule or the collecting duct. So this is the lumen, and in here is filtrate. Okay, so when the filtrate goes into the distal convoluted tubule and it's going through, it's a lower osmolarity. It could be as low as 100 milliosmoles. And then it can change over the distance of that to become more concentrated. If you drink a whole lot of water, it's not going to be that concentrated when it comes out as urine. It's going to be real light. If you hardly ever drink water and that type of thing, then it'll probably be more concentrated. So as it comes in, we'll say that it's 100 milliosmoles. So it's coming through the distal convoluted tubule and the connecting duct at about 100 milliosmoles. So that filtrate is coming in through, and blood pressure is low. So the posterior pituitary, post-pit, is signaled to dump in ADH by the hypothalamus. Remember, the hypothalamus makes ADH, but it's stored in the posterior pituitary, and then the hypothalamus tells posterior pituitary to dump it into the blood. So now we have ADH. So ADH is in here, coming into the blood. And what ADH does is on the collecting duct, and the collecting duct mainly. The collecting duct is not permeable to water in its normal state. And the cells on the collecting duct, which are, cuboidal cells, have receptors on them because this is a peptide type of hormone. And this hormone, ADH, is going to come in and bind to the receptor. And when it does that, inside these cells, so in these cells are vesicles. And in these vesicles contain aquaporins. And if you remember that word, that's something we kind of talked about in AP1 when we're talking about how things move. And we're talking about water and osmosis and all that. And I said that there were special channels for water called aquaporins. And I also said that they were really prominent and useful in the kidney. Well, here's where they are. So the cell takes these aquaporins that are in these vesicles and bring them to the surface and deposit them into the luminal side here. So now we've got aquaporins in here and this is on a tube that is impermeable to water. So it is now permeable to water. So now we have this 100 milliosmol filtrate coming in here. And don't forget, keep in mind that the collecting duct goes down into that weird medullary osmotic gradient. So it's coming into here, and that means that it's sitting in an area that's becoming more and more concentrated. The osmolarity is going up. So that 100 milliosmol filtrate is going into an area that's, say 400, 500, 600, 700, 800. It's going down here. So as it does that, the water that's in the filtrate is going to start to come through the aquaporins. And that water is going to go back into the blood. When the water goes back into the blood, it increases blood volume, which increases blood pressure. And when the blood volume goes up, pressure goes up, the vessels now feel stretch. And once they're feeling stretch, then they stop telling hypothalamus that they're not feeling stretch. So this is how ADH works. ADH tends to work with another hormone called aldosterone, which we'll go over next.